Hello, this is John Miares. In the last lesson, we looked at things like the Pythagorean identities, the reciprocal identities, and the negative angle identities. Then we started using them to solve different types of trigonometry problems and began exploring the ideas of doing proofs involving these identities. In this lesson, and in the next, we're going to expand on those ideas and play with a few more identities. In particular, we're going to start looking at identities involving the sum and difference of two angles, which we could label as x plus y, alpha plus beta, or theta plus phi. The most important thing that I need to emphasize with these identities is that when I'm looking at the sine of the quantity x plus y, or the cosine of the quantity x minus y, the distributive property as we know it does not apply. This does not become the sine of x plus the sine of y. This bottom one does not become the cosine of x minus the cosine of y. There's actually a lot more to this, and the order of operations is going to dictate how we handle it. What we're going to be doing here is taking two different angles, then either adding them together or subtracting them before taking their sine or cosine. Let's say I have these two angles here. Angle X is something in quadrant 2, and based on its slope, it looks like the angle measure must be something slightly bigger than 135 degrees. Meanwhile, angle Y has its terminal side in quadrant 3, and this looks like it will have a measure that is slightly bigger than 225 degrees because the slope of this segment is going to be slightly bigger than 1. If I were to add those two measures together, something slightly bigger than 135 degrees and something slightly bigger than 225 degrees, the angle we'll end up with is something slightly bigger than 360 degrees, which will end up in quadrant 1. So if I were to take the sine or the cosine or the tangent of that angle x plus y, those angles will generate, when I apply the right trig functions, all positive values for sine, cosine, and tangent. If I was to just look at the sine of x and then the sine of y and add them together, that's not going to happen. Anyway, let's see what the identities look like here. The sine of the sum of two angles x and y is going to equal the sine of x times the cosine of y plus the cosine of x times the sine of y. Now, I could have called these angles anything. I could call them A and B, alpha and beta, theta and phi, but ultimately what it breaks down to is that if I'm taking the sine of the sum of two angles, then I want to take the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. Now, understandably, this is not intuitive at all, and while memorizing these could be helpful, I don't know of any part in the course where memorizing these identities is going to be a necessity. In preparation for an upcoming quest and for the final exam, these formulas will be given to you on a reference sheet. The second identity, the sine of the quantity x minus y, is very similar, except there's going to be a minus sign instead of a plus sign between the two products of the terms. For cosines, the pattern is going to work a little differently. The cosine of the quantity x plus y is going to start by taking the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second. If I was to subtract the two angles, then the sign between these products changes from a minus to a plus sign. Now, there's probably two questions you're thinking about in the back of your head. Well, three, if you include the fact that I already answered the question about whether or not you have to memorize these identities. First, will you need to know how to prove that these identities are true? If you are pursuing the honors option, you will be expected to know how to prove that these identities are valid and write them up as part of your honors requirements. For most of you students, no, you will not have to prove these identities themselves. You will, however, be asked to use these identities as parts of other proofs. The second question you might ask might be about the tangent. Why haven't I given you identities for the tangent of x plus y or the tangent of x minus y? Well, those identities exist, I just hadn't gotten around to them yet. For the tangent of x plus y, you'd want to take the tangent of x plus the tangent of y and divide that by 1 minus the product of the tangent of x and the tangent of y. For the difference between two angles x and y, when I apply the tangent rule, I'm just going to change the signs again. Now, although I'm saying that you won't have to memorize these identities, you will be using them enough to where you want to make sure that you have them written down somewhere handy. These are typed up in the handout notes for Unit 5 provided in the Week 9 content folder. But if you want to have your own notes for them, that's fine too. As we go through different examples in this section, we're going to be referring back to these quite a bit. So as long as you have something handy to keep with you to help you, that would be best. Now let's see how we might use the identities to solve problems on our homework. Suppose you are asked to determine the exact value of the sine of 15 degrees without a calculator. As a reminder, a calculator can, at best, get you the decimal approximation, but it will not give you the exact value of the expression. What we're going to do is try to look at the 15-degree angle as the sum or difference of two angles that are special angles or mad-minute angles, which we do happen to know the exact value of. With 15 degrees, we have a couple of options. We could say that 15 degrees equals 45 minus 30, or we could say it equals 60 minus 45. Either choice will give us the same answer, but what we're going to do for this particular example, which says I'll take the sine of the difference between two angles, so I'll have the sine of the first times the cosine of the second minus the cosine of the first times the sine of the second. We're going to start by assuming that our first angle x will be 45 degrees and our second angle y will measure 30 degrees. Substituting these values into the expression, we get the sine of 45 degrees times the cosine of 30 degrees minus the cosine of 45 degrees times the sine of 30 degrees. From here, let's substitute in what we know about each piece of this. The sine of 45 degrees is the square root of 2 over 2. The cosine of 30 degrees is the square root of 3 over 2. Now we need to subtract the cosine of 45 degrees, which is the square root of 2 over 2, and multiply that by the sine of 30 degrees, which is 1/2. Now let's try to simplify this. The first term, when we multiply those fractions, becomes the square root of 6 over 4, while the second fraction is going to be the square root of 2 over 4. They already have a common denominator, but the radicals themselves have to stay separate, which will lead us to a final answer of the square root of 6 minus the square root of 2, all divided by 4. Now, what if we had used x equals 60 degrees and y equals 45 degrees instead? What you should notice when you substitute those values in and apply the identity, what you should notice is that you're going to get the same results. The sine of 60 degrees is the square root of 3 over 2. The cosine of 45 degrees is the square root of 2 over 2. And the second piece, the cosine of 60 degrees is 1/2. And the sine of 45 degrees is the square root of 2 over 2. Here is a similar problem. Here we're asked to determine the exact value of the tangent of 75 degrees. Just like we did in the last example, we want to find two mad-minute angles that we can combine through addition or subtraction that will get us a total of 75 degrees. We do have some options to choose from. Probably the easiest one to see right away is to take 45 plus 30 to get 75. But you may wish to get creative and take 120 minus 45 to get 75 degrees. I would probably be more inclined to use the first choice instead of the second because the angle measures 45 degrees and 30 degrees are all in quadrant 1. So I don't need to worry about one of the values coming out negative and losing a sign somewhere. The identity, as a reminder, is that the tangent of x plus y equals the tangent of x plus the tangent of y, all divided by 1 minus the product of tangent x and tangent y. If we now say that x equals 45 degrees and y equals 30 degrees, then the tangent of 45 plus 30 can be re-expressed as the tangent of 45 degrees plus the tangent of 30 degrees, all divided by 1 minus the tangent of 45 degrees times the tangent of 30 degrees. Now let's substitute what we know. The tangent of 45 degrees is 1, and the tangent of 30 degrees is the square root of 3 over 3, which is going to look like this mess here. The burning question of the day, can I leave this as my final answer? Unfortunately, no. We need to simplify this result as far as we can take it, which means not having an answer which is a complex fraction and not having an expression with square roots in the denominator. So where do we begin? First, let's try using a common denominator within each part of the fraction. Both the big numerator and the big denominator have a root 3 over 3 in it. So what I would recommend doing is to turn each of those ones, the 1 plus root 3 over 3 and the 1 minus root 3 over 3, into 3/3 by multiplying by 3 over 3. Then we can use the common denominators to simplify the expression a bit. In that big numerator, we can get this rewritten as 3 plus the square root of 3 over 3. And in the denominator, you'll get 3 minus the square root of 3 over 3. Next, we want to recall the rule that says when you divide a fraction by a fraction, you want to multiply by the reciprocal of the one you are dividing by. When you do that, those 3's are going to cancel and leave you with 3 plus the square root of 3, all divided by 3 minus the square root of 3. Now this result here certainly looks a lot better than what you see right above it, but we're still not done yet. We're not allowed to leave this square root of 3 in the denominator of the fraction. It's not considered proper form. So we can get rid of it by multiplying the numerator and denominator, the top and bottom of this expression, by the conjugate of the denominator, 3 plus the square root of 3. In the numerator, after we apply the FOIL method, we'll get 9 plus 6 square roots of 3 plus 3. In the denominator, the radicals will fall out because the difference of squares pattern will cancel out your middle term. You'll be left with 9 minus 3. Simplifying both the numerator and denominator a bit, we'll get 12 plus 6 square roots of 3 all over 6. For the cleanest possible answer, we can factor out and cancel a 6 out of both the numerator and denominator to get our final answer as 2 plus the square root of 3. So this one wasn't very pretty, but what I will say is that you always just want to start with the identity that you know you need to work with and then substitute in what you know. The hard part is making sure that your algebra skills are strong enough to deal with the simplification of these terms, especially when it comes to working with complex fractions, getting radicals simplified, and multiplying by conjugates to rationalize denominators. There's a couple of problems on the homework that ask you to work with the identities backwards. For example, here we are asked to use identities to simplify and evaluate the following expression without a calculator. We want to take the cosine of 22 degrees times the cosine of 68 degrees minus the sine of 22 degrees times the sine of 68 degrees. Again, your first instinct is probably that this problem is not possible to do without a calculator because none of those angles in this problem are mad-minute angles. But we do have one of our identities that says the cosine of the sum of two angles, x plus y, will equal the cosine of x times the cosine of y minus the sine of x times the sine of y. If we were to try to apply that identity backwards, we could say that our given expression, cosine of 22 degrees times the cosine of 68 degrees minus the sine of 22 degrees times the sine of 68 degrees, could simplify to the cosine of 22 plus 68 degrees. Well, simplifying inside the parentheses, 22 plus 68 is 90. And now we do have a mad-minute angle here. The cosine of 90 degrees is 0. And that's all there is to this problem. All we really did was recognize that we could use these identities in reverse. Now let's try doing a proof that uses these identities. Here's one that is very similar to one on the homework. Suppose we want to prove that the sine of pi over 2 minus x equals the cosine of x. Now, all of the examples we have done so far have been in degrees. But again, there is absolutely no reason why we can't be having some of these problems show up in radians. Pi over 2, remember, is the same as 90 degrees. So if you want to look at this as the sine of 90 degrees minus x and prove that equals the cosine of x, the process isn't going to be any different. We still want to use this identity, which says that the sine of the difference between two angles will equal the sine of the first times the cosine of the second minus the cosine of the first times the sine of the second. Starting with what we are given on the left-hand side of this equation, we can substitute our first angle pi over 2 and our second angle x and apply this identity to the best of our ability. Doing so gives the sine of pi over 2 times the cosine of x minus the cosine of pi over 2 times the sine of x. The advantage we have here is that pi over 2, or 90 degrees, is a mad-minute angle. and you should have memorized those values by now. The sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So that leaves us with 1 minus, so that leaves us with 1 cosine x minus 0 times the sine of x. Since 0 times anything is 0, then this will simplify to be just the cosine of x. So that shouldn't have been so bad. But what we've essentially proven here is that the cosine of an angle will always equal the sine of its supplement, which is something that we probably already knew, at least intuitively. After all, we know from our different tables that the sine of 60 degrees would equal the cosine of 30 degrees, or the cosine of 90 degrees equals the sine of 0 degrees, or the sine of 45 degrees will equal the cosine of 45 degrees, and so on. What we've done now through this proof is formalize this. And now we can definitely say with 100% certainty that through using these various trig identities, this relationship between the cosine of an angle and the sine of its complement are going to be equal. It isn't just that it's going to seem to be true because we've observed it looking at various tables, but we can now be confident that this is always going to be true. Let's do a little variation on a theme here. Suppose you were given something that looked like this, where you were asked to find the exact value of the cosine of a quantity inverse sine of negative square root of 3 over 2 plus the inverse cotangent of 3/4. This looks pretty intimidating, but in reality, it isn't. Ultimately, what we have is the cosine of the sum of two things. And we have an identity for that. The cosine of the quantity x plus y will be the cosine of x times the cosine of y minus the sine of x times the sine of y. What we also need to realize is that when we're looking at the inverse sine of the negative square root of 3 over 2, that's just going to be some angle theta in quadrant 4. If we're using the unit circle perspective, we'll see that I have an opposite side that is negative square root of 3 over 2 and an adjacent side of 1/2 and a hypotenuse of 1. Although we should know the value of this angle to be negative 60 degrees, I'm less concerned about the measure of the actual angle. So for now, we're just going to call this angle theta. Meanwhile, to look at the inverse cotangent of 3/4, what we're considering is a reference triangle in quadrant 1 that has an adjacent side of 3 and an opposite side of 4. Using the Pythagorean theorem, we can compute the hypotenuse length to equal 5. While this isn't one of our mad minute angles, this is a triangle we have worked with before. So we're just going to label the reference angle here as phi. What we can do now is rethink how our identity is going to work, and instead of using x and y, we can think of the two things being added together as two angles, theta and phi. So the cosine of the quantity theta plus phi is going to equal the cosine of theta times the cosine of phi minus the sine of theta times the sine of phi. Now, the values of each of these expressions can be taken directly from these reference triangles we've constructed here. The cosine of theta will be 1/2. The cosine of phi is 3/5. Minus the sine of theta is the negative square root of 3 over 2 times the sine of phi, which is 4/5. Now let's multiply these fractions and simplify where we can. 1/2 times 3/5 becomes 3/10, while the negative square root of 3 over 2 times 4/5 becomes 4 square roots of 3 over 10. The two negatives within the expression will turn that into a plus sign. Combining the two fractions together with the common denominator will give you a final answer of 3 plus 4 square roots of 3 all over 10. For the next example, we are going to do something very similar to the last example, but perhaps go a bit more abstract. Suppose you are asked to write the given expression in terms of x and y only, where you have the sine of the quantity inverse sine of x plus inverse cosine of y. Again, from the outset, this looks really scary, but when you break it down into smaller pieces, it's really not that bad. Remember, when you take the inverse sine of x, what you're ending up with is some angle theta. In reverse, that's the same as saying that the sine of some angle theta will equal x. Similarly, computing the inverse cosine of y is also going to generate an angle which we will call phi. So with that, we could also say that the cosine of angle phi will equal y. Let's try drawing a picture of a reference triangle if that will help it visualize for you better. Here's angle theta. What we're saying is that the sine of angle theta equals x, which I could rewrite as x over 1. That means the opposite side could be labeled as having length x, while the hypotenuse will have a length of 1. Using the Pythagorean theorem, the adjacent side will have a length that is equal to the square root of the hypotenuse squared minus the opposite squared. And that will simplify as the square root of the quantity 1 minus x squared. Now let's draw a different triangle for our other angle, phi. Since here we're saying that the cosine of phi equals y, then our adjacent side will equal y, and our hypotenuse will equal 1. Using the Pythagorean theorem on this triangle, the opposite side will simplify as the square root of the quantity 1 minus y squared. Now that we have our reference triangles in place, let's see how that can simplify matters. The sine of the sum of two angles, x and y, or in this case, theta and phi, can be written as the sine of theta times the cosine of phi plus the cosine of theta times the sine of phi. The values of each of these pieces can be read directly from our reference triangles. The sine of theta is just x over 1, and the cosine of phi will be y over 1. Of course, we knew this part from the setup of the problem. The cosine of theta will be the adjacent over the hypotenuse in the upper triangle, square root of 1 minus x squared all over 1, and the sine of phi is going to be the opposite over hypotenuse in the lower triangle, which will be the square root of 1 minus y squared over 1. Now, all of these are over 1, so it won't take much to simplify this. Our final answer will just be the products as shown, x times y minus the product of those two radicals. So the key takeaway from these problems is to construct reference triangles and to use the Pythagorean theorem to find the missing side lengths, whether you're given values of the side lengths like on the previous slide, or if you're just given the variables like on this slide. Once you have your reference triangles and you know what identity you want to use, just read the values you want off of the reference triangles, substitute them to the identity, and simplify the results. One of the problems on the homework asks you to apply the difference quotient here, and it really isn't a very consequential result at this point, but it will have an impact in your study of calculus. Suppose you are asked to apply the difference quotient, f of the quantity x plus h minus f of x, all divided by h, when the function you're working with is the sine of x. Until you get to calculus and until we actually start doing more with difference quotients, I don't know that the final answer to this problem will leave a good taste in your mouth. But this is what we're asked to do on the homework, so let's get to it. We have to compute f of x plus h minus f of x and divide the whole thing by h. Knowing that in this case, f of x equals sine of x, that will become the sine of the quantity x plus h minus the sine of x all over h. Using the sum identity for sine, we could expand that first piece into the sine of x times the cosine of h plus the cosine of x times the sine of h. Then we would subtract the sine of x and divide the whole thing by h. From here, unfortunately, there's not much else we can do. We could rearrange the terms a bit to take a sine of x out of the first and third terms in the numerator, and that will get you this. But until we know a little bit more about what h is supposed to stand for, there really isn't anything more we can do here. Which has me wonder why the author is asking you to do this exercise at this point to begin with. Maybe he knows you're going to see this in calculus again, and since he wrote the calculus book you're going to be using, assuming you take Math 151 at LCC, he's just giving you a foretaste of things to come. In the final example, I want to show you something that will more likely than not be on the next quest. Suppose you're told that the sine of angle alpha is 3/5 and the terminal side of alpha lies in quadrant 2. Then you're also told the cosine of angle beta equals -3/5 and angle beta has its terminal side lying in quadrant 3. From here, you might be asked to evaluate the sine of alpha plus beta, the cosine of alpha plus beta, or the tangent of alpha plus beta. Our approach to this problem is going to be very similar to what we did a few slides earlier, where we constructed reference triangles to figure out more information about alpha and beta. So here are our two triangles that I'm going to be working with. In quadrant 2, we have angle alpha, and we're going to label the sides in such a way that the sine of angle alpha is 3/5. This makes our opposite side y be 3 and our hypotenuse be 5. The adjacent side will equal -4, partly because this is a 3, 4, 5 triangle. We know the length of that side has to be 4, either positive or negative, but we also know it has to be -4 because we're in quadrant 2 and x values are always negative in quadrant 2. In quadrant 3, we want the cosine of angle beta to be -3/5. So the adjacent side x will measure -3. The hypotenuse will equal +5. The opposite side will be -4. Again, this is a 3, 4, 5 triangle, but being in quadrant 3, our opposite side y must be negative. Now that we have our reference angles in place, let's expand out our identities. The first one, the sine of the quantity alpha plus beta, will equal the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Reading these values directly from the triangles, we see that we'll have the sine of alpha is 3/5 times the cosine of beta, which is -3/5. Again, both of those values were actually given to us in the original part of the problem, plus the cosine of alpha, which is -4/5, times the sine of beta, which is also -4/5. Multiplying out these fractions will give us -9/25 plus 16/25, which when combined becomes 7/25. For the cosine of alpha plus beta, the identity will turn into the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Plugging in these values based on reading them from the triangle will give us -4/5 times -3/5 minus 3/5 times -4/5. Simplifying each piece will give us 12/25 minus -12/25, which becomes 24/25. For the tangent of alpha plus beta, we actually have two different approaches we could use here. First, we do have our identity for the tangent of the sum of two angles, which says we take the tangent of the first plus the tangent of the second, all divided by 1 minus the product of the tangent of the first and the tangent of the second. However, that's not the only approach that we have to use here. An alternative approach might be to take the tangent of alpha plus beta and set it up as the sine of alpha plus beta divided by the cosine of alpha plus beta, essentially using the special reciprocal identity for tangent, saying tangent equals sine over cosine. Since we've already computed the sine of alpha plus beta and the cosine of alpha plus beta, we could use those two answers to compute the tangent of alpha plus beta by just dividing the results. So let's do just that. Let's take 7/25 and divide it by 24/25. When you divide a fraction by a fraction, you want to flip and multiply by the fraction on the bottom, so it becomes 7/25 times 25/24, which when you cancel the 25s reduces to 7/24. So again, we approach this by constructing reference triangles based on the information we're given right after the word suppose, and then we're going to use those reference triangles when applying the identities. This approach is going to get you through several of the problems on the homework and on the next homework. So this was a fairly short presentation, but admittedly, there was a lot in it. I was tempted to try to put together section 7.2 and 7.3 into a single video, but the content is different enough that I think it would be best for you to give these problems in section 7.2 a try before attempting to dive into section 7.3. In fact, 7.3 will be very straightforward if you are able to make sense of what we've done here in section 7.2. Here are the problem challenge problems for section 7.2. Give these a shot and come to the next ORT session with your questions. Thanks for watching, and we'll see you all soon.